Now you may remember that we dropped an apple from 3 meters and that we calculated the gravitational acceleration given the time that it takes to fall. That was one of the things you did in your assignment. We had 781 milliseconds, I think. And out of that you can calculate g, right? Because you know that 3 meters is 1/2 gt squared. So I give you the 3 with an uncertainty, I give you the time, 781 milliseconds, with an uncertainty of 2 milliseconds, which we allowed, out pops g. So I asked Dave, what is the effect of air drag on this apple? Was it a responsible thing for us to ignore that? The apple has a mass of 134 grams. It's easy to weigh, of course. So this was our apple during our first lecture. M is 134 grams. It's almost a sphere, really. Not quite, but almost a sphere, and the radius is about 3 centimeters. And that leads to a terminal velocity, which you can calculate if you want to, using the v squared term, but I was not interested in that. I wanted to know how many milliseconds is the touchdown delayed because of the air drag. And Dave made the calculations, and he found that that is 2 milliseconds from 3 meters. From 1.5 meters, it's almost nothing. And the reason why it's almost nothing from 1.5 meters, you see, when you throw an apple in air, it's really in regime 2. So you're really dominated by the speed square. And the first 1.5 meters, it doesn't get a very high speed yet. The speed grows linearly, and so it is the last portion where you really get hit by the air drag by the v squared term. 2 milliseconds from 3 meters. So if h is 3 meters, there is a 2 millisecond, let's call it delay. So we were on the hairy edge of being lucky and unlucky. If you really want to recalculate the gravitational acceleration using our data, you should really subtract the 2 milliseconds from the time. On the other hand, since we allowed a 2 millisecond uncertainty, we really weren't too far off.